Well, today I wanted to talk to you about electric car racing anyway. I think it's pretty sweet. I think it's the future of racing. But when we talk so much about normal run-of-the-mill batteries, like electric vehicles you can go and buy off of a car lot or on the internet at this point, what's the difference between that battery and designing a battery for racing? Because they seem to be very different.
Racing batteries, unlike production batteries, have a different cost availability, which enables new materials. And they also don't require a manufacturing process that is mass production friendly and easy to repeat. They can use niche manufacturing processes. This is because the production is low.
So racing batteries are artisan.
Yes. In in a normal what you call a run-of-the-mill EV, like let's say it's a Leaf or a Bolt or a Model 3 or something, the battery is designed with lowest cost to manufacture, lowest labor to manufacture, lowest parts cost to make something that is safe and long-lasting. And that's a very difficult thing to engineer for, and respect to their achievements. With a racing battery, you care less about cycle life. You care less about maybe fast charging is irrelevant, for example. What you need is even safety tolerance, perhaps. You have a higher envelope for cell behavior.
That seems really weird coming out of your mouth. Do you want to elaborate on the safety between a normal run-of-the-mill
Well,
battery versus a racing
in a
battery?
yeah, in a battery pack that you're trusting to be, driven by your grandma and whatever, you want to be sure that she could get out of that car in time if there was a problem. So even in a worst case sort of situation, but in a racing battery, you're lucky that you're usually required to already be in a fireproof suit. And you also, unlike in a situation where maybe if you were in a car wreck, you would have to wait for medical care to get you out of the car. In a racetrack situation, there's, often 3 or 4 ambulances at the track, and they are ready to help if there's a problem.
But you still need to care about the energy release at some point.
Yeah, ideally you don't want to be barbecued in your race car. So that's why we'll, even on this pack for modifying the Plaid Model S, we'll be doing arc calorimetry run, known as accelerated rate calorimetry. So we'll quantify the joules of thermal energy release, the gas volumes and gas release rates, as well as sample gas to put through the mass spectrometer to determine that we don't have a unacceptably toxic type of toxic to human species of gas being produced. Also, when you put the pack into the vehicle, I'm going to have a firewall between the passenger compartment and the vehicle. And by doing calorimetry tests at a small scale, we can validate that it will be resistant, the firewall will be resistant to entering the passenger chamber.
So what I'm hearing is that a racing vehicle battery specifically has one job, which is to release energy through the powertrain and things like charging, things like repeatable safety, things like it living a long life.
Those are all secondary.
Yeah.
Normally, you've got to put safety as number 1, and most companies put cost as number 2 behind safety, and then performance and things fall where they fall. But that's not how to win races in racing. You have to put performance as number 1. And so the metric you care about for many types of racing is kilowatts per kilogram, which is what we're testing for this Plaid application. In other EV racing, say you're doing road racing or endurance racing or long hill climbs that last 10 minutes, in those situations you have to design a battery around different parameters than something like our drag racing record target. We only need to preheat our battery, as one example. We'll be preheating to around, say, 45 Celsius before the run. This is to reduce our impedance. And because the duration of the run will only be some amount of time in the 8-second range, we won't have a duration where the cells will reach an unsafe temperature before the end of it, at which point they can cool back down to 40C. in the extended racing, road racing, endurance racing, even long motocross racing, the pack has time to heat up and even overheat. And in those types of situations, it's much different than drag racing or hill climbs, where instead of just having heaters added, you also have to add some method of effective heat transport out from your cells.
So you're saying that when you heat up your battery for drag racing, it actually cools during the time that you're racing it?
Well, I mean, during its discharge, it will gain. For example, when we were discharging at 70 Celsius, we were gaining about 3 degrees Celsius per second. So during an 8-second run at 70 C, you would expect to gain, around 24 degrees C. So if we started it from a cell at, say, 40 degrees Celsius, we would expect it to end at around 64 Celsius at the end of the drag run.
So how do you balance all these different factors that go into a design for a race pack, right? You have the
So
performance, you have the discharging.
in a race pack, you're balancing weight, uh, and it becomes a guiding factor, as every pound extra that your vehicle has to carry is something you left on the table for someone else to set a faster record with. So this is why, in a racing situation, you may use aluminum bussing, for example. In production cars, they also use aluminum bussing sometimes, but it's for a different reason. They're doing it as a cost savings, and in a racing application, when you use aluminum bussing, you're using it because even though it only has around 60% of the electrical conductivity of aluminum, it's such a significantly lighter fraction of the weight that it still ends up being an advantage in conductivity per unit mass of bus bars. So we'll likely be using aluminum power busing for this application.
What are some of the biggest challenges when designing a battery pack for racing?
Well, depending on the type of race, sometimes vibration and G-shock is a major factor. Even in a situation where it may be a short duration race, it can have very aggressive G-shock. The reason why it's so important is if you have vibration and chafing issues, you can have an arc fault type of situation that consumes your battery in a electrical plasma driven fire that is fierce. So it's critical that you design around the loads. We're lucky in the situation for our application on a drag strip. We have only low G loads. Our acceleration will be around 1.4 G, and hopefully we can hold that longer than any other Tesla's ever held 1.4 G. But at that rate, we're not in a chafing and not in a chronic chafing and vibration situation. If we were, say, desert racing or motocross racing, and the bike gets used for many years, then vibration and chafing effects are much more pronounced, as it's something that accumulates with time and cycles. So that's another advantage for a race pack, is that the whole life expectancy of the pack may only be a half dozen or a dozen racetrack events for the life of the vehicle. And so that means the battery may only have to survive, say, hours of use for its entire lifespan to be a successful, to accomplish all the goals and objectives you had for it.
I made the smiley face because you talk about things like plasma arcing just in a very gentle way when it's like really one of the most violent events I've ever seen.
This pack that we're building for the Plaid, if it were to have a dielectric failure and an arc flash event, it will be capable of a sustained discharge current of around a megawatt, and if it were hard short circuited, it would be a considerable amount of arc blast energy. Lorentz forces, magnetic forces from arc flash, will locally, the plasma heats the metal into a liquid, and the magnetic repulsion from the electrical currents flowing through that molten liquid cause the droplets to eject from magnetic force at supersonic speeds. When it transitions from subsonic to supersonic ejecta, it becomes an arc flash or an arc blast. Arc blast being when it's over supersonic or at supersonic.
Thank you.
You're welcome.
I feel like we wouldn't be having a normal conversation without you using the word supersonic.
Yeah, I mean, who doesn't like 10 to 50,000 degree supersonic plasma ejection. That's why we want to have our dielectrics well protected for the application. We're lucky that in this drag application, we don't have to protect things as well as, say, a desert truck's application. Impedance is what throttles your horsepower. You know, you can look at impedance as the resistance to current flow. So you want, you know, your dream world racing battery would have a resistance of 0. It would have no impediment to current flow. So it would just maintain a voltage and you could pull however much current you needed from it until the pack was empty.
So the impedance change over that battery's life, how does that impact the performance?
That's another really good point you brought up about a racing battery. They will climb an impedance faster than most any other cells. They start out with an extremely low impedance, but to get such a small battery, you know, for example, we were discharging over 100 amps on this 1.4 amp hour cell yesterday. And for that tiny little cell to discharge 100 amps, you know, that's 300 watts of power from that cell, or this 6S stack would be around 1.8 kilowatts that we were pulling from a battery this size. For such a small, tiny, lightweight package to pull so much power, it has to have the surface area and surface reactivity of a larger cell. And so by having such finely divided surface and electrolyte and electrode interfaces, they have the things like the side reaction rate and gas production rate and impedance climb rates of a bigger cell, because they have the surface area that's wetted by electrolyte to react of a bigger cell. And so for this reason, cells with extremely high C rates like this will climb an impedance faster than the cells that you would have in your normal EV, where they're targeting an acceptable impedance after, say, 8 years or 10 years or 15 years. Whereas a cell like this made for a drone racing application may only maintain its impedance for, you know, say 1 year, 2 year before its reactivity, because it's only got such a small envelope for gas and other side reaction products to go into, and yet it has the surface reactivity of you know, a cell that can deliver 100 amps.
And this impedance change and climb over time, how does that impact the thermal management of the battery?
Okay, it will directly increase. So you'll not only lose horsepower as its impedance increases with time, but the fraction of power that was going into your motor, now as it grows in impedance, a higher fraction of that chemical potential energy that you stored will be going into heating your cells. So in one of the examples we gave earlier, we showed the difference between a 2 milliohm and a 3 milliohm cell, and it turns out it's the difference between 500 amps or just 333 amps to sag both cells to the same 3-volt safety limit. And this is why every milliohm you can cut out of your cell resistance directly translates to the ability to have a smaller, lighter, overall higher performance electric vehicle for the purpose of setting records and things.
Thank you for you're explaining impedance in many different ways, and it's starting to click on like all the different parts.
Great.
And why it's like the core metric to understand, especially when building a racing vehicle.
So if this cell was new and it was 5 milliohms, and after a year or two it was 7.5 milliohms, then instead of only increasing by 3 degrees per second when it's under 100 amp discharge, it would increase in temp at around 4.5 degrees per second. And
Pretty hot.
yeah, this is a significant increase in the rate that it will heat up, and that means that pack can no longer discharge for as long before reaching its safe temperature max cutoff. So that's why as impedance grows, your performance decreases. And also if you care about energy efficiency, then the goal was never to waste your energy in the battery getting hot. It was to turn the wheels harder. And so as impedance goes up, you have more of that chemical potential energy you stored just heating your cells.
I think that leads into the question that I have, which I think many people would want to know. What innovations are being made to reduce impedance and improve performance in racing vehicles?
Well, there's many ways to accomplish it, but some have more painful drawbacks than others. So one of the methods you can use is to increase your porosity and surface area. This allows higher electrode channeling, wetting. It also, by reducing electrode density, you lose energy storage. You lose energy density because those free electrolyte channels, while they help to improve your C rate, they don't help to store any energy for you. There's other tricks by making the electrode particles more conductive to each other. So there's different binder materials people add, or, say some fraction of 1% carbon, single wall carbon nanotubes, or graphene oxide additives, which are very common in cells.
Thank you for letting me cut you off here. You're talking about innovations in impedance and reducing that, and can only be done in cells, right? It's not anything a pack builder could do. This is a cell level innovation.
The pack builder, if he does everything perfectly, can not, ever drop below the cell impedance.
Right.
You can make it to where your interconnect system is so low resistance, and we will be doing this, that it's only, say, 1 or 2% of your total impedance of the pack. But if you want to get below that, it requires improving the cell. Those techniques that I mentioned, like single wall carbon nanotube additives, graphene oxide additives, these are conductive modifiers that improve electrical conduction between the particles, forming your electrodes, so that you have lower voltage drop and lower resistance between these points of electrical potential energy storage, electrical chemical potential energy storage, and your foil current collectors, which carry that current to the tab. You can, a wise battery mentor of mine, Keith, once told me, there's never a time you can't trade capacity for impedance. You can't trade capacity for C rate.
And that's the balance that is made a lot of times in run-of-the-mill EVs, right?
That's right. With these packs in particular, we're using them because they're some of the highest power density batteries in the world, but they're not as high power density as they could be if they didn't have to fly for a long time too. So these are made for a drone pilot to complete a drone race that could last a minute or two. And if we were to take this cell and say, I can live with half the energy,
right?
Give me more C rate.
Yeah.
Then they can thicken the foils. They can add more conductive modifiers. And other tricks you can do is higher surface reactivity electrolyte solvents and bases and additives. These have their own downsides of usually accelerated gas production or other issues. But you can, essentially you're fast forwarding time thermokinetically to age the cell when you run those very fast electrolytes. It's one of the reasons why cells like this have a short calendar life. You make them and then you need to use them in a year or two because
so these are
time
great.
is reacting with them.
These are great for playing around with an existing vehicle. Mm-hmm. But when our friends write us a blank check, basically, you would start at, I want to design a cell specifically for this race.
And you wouldn't have them fit into little 6S packages with heat shrink either. You would get the cell bare from the manufacturer. And to buy, even perhaps for the Plaid sized scale of pack build, we may order cells direct from the manufacturer too.
Cool. Thank you.
Yeah. That lets you package them in a way that is appropriate for the voltages and power levels and vibration and shock levels that your application may require.
Yeah. Cell innovations for racing.
Yeah. And if the manufacturer is willing to, we could say, how about instead of having this for 1.4 amp hour pack, let's make it a 1 amp hour pack at the same size and weight, and put all of that freed up, all of that freedom you have in the cell now into everything you can do to drop resistance.
Thank you for sitting with me to talk about your project that you're working on with the Plaid. And I'm excited to see how your testing goes and which cell has the least impedance.
My pleasure. I'm very excited for the testing to complete too, and to find out which of these we'll be buying more of and running safety tests, and then building into sub-modules, modules, and finally the booster pack.
Cool.